In this presentation, we will study the basic fundamentals of sound needed for understanding sonar. We will first see how sound is generated and how it travels through a medium. Then we will discuss important sound wave properties such as frequency, amplitude, wavelength, and longitudinal propagation. Finally, we will introduce the main acoustic quantities used in sonar, including sound pressure, frequency, wavelength, sound speed, intensity, and sound level. This video is presented by Professor Gottapu Sasibhushan Rao. Sound is produced when an object vibrates. This vibration disturbs the surrounding medium and generates a mechanical sound wave. For example, in the human voice, the vocal cords vibrate. In a loudspeaker, an electrical signal makes the diaphragm vibrate. Musical instruments and natural sources such as thunder also produce sound through vibration. Now look at how sound travels. The particles of the medium do not travel with the wave over a long distance. Instead, they vibrate back and forth about their mean positions. Energy is transferred from one particle to the next, while the sound wave moves forward. Therefore, sound needs a material medium such as air or water. It cannot travel through vacuum. In sonar, water acts as the medium, and sound travels through it mainly as a longitudinal pressure wave. Now let us look at the important properties of these sound waves. Properties of sound waves. Let us begin with the sound spectrum. Sound is classified mainly by frequency. Below 20 Hz is called infrasound. The approximate human hearing range is 20 Hz to 20 kHz. Above 20 kHz is called ultrasound. Sonar may use audible or ultrasonic frequencies depending on the application. Now consider amplitude. Amplitude indicates the strength of the vibration. A larger amplitude generally corresponds to greater loudness. Next is frequency. Frequency is the number of cycles completed in 1 second. A low frequency gives a low pitch, while a high frequency gives a high pitch. So, amplitude is mainly related to loudness, whereas frequency is related to pitch. The transverse wave figure is shown only for comparison. In a transverse wave, the particles vibrate perpendicular to the direction of wave propagation. But sound in air and water is mainly a longitudinal wave. In a longitudinal wave, the particles move back and forth in the same direction as the wave travels. This produces alternating regions of compression and rarefaction. In a compression region, the particles are closer together, so pressure and density are high. In a rarefaction region, the particles are farther apart, so pressure and density are low. The wavelength, lambda, is the distance between two successive compressions or two successive rarefactions. Therefore, in sonar, sound propagates through water as longitudinal pressure variations and returns from a target as an echo. Basic acoustic quantities for sonar. Now that we understand how sound is produced and propagated, we need measurable quantities to describe it. First, acoustic pressure varies with time and is represented by P of T. For a sinusoidal sound wave, the equation shown here gives the variation of pressure with time. The pressure amplitude represents the maximum pressure variation. The frequency, F, tells us how many cycles occur per second. The period, T, is the time taken for one cycle, so frequency is the reciprocal of period. Next, look at the spatial wave. The wavelength, lambda, is the distance between two successive points having the same phase. Sound speed, frequency, and wavelength are related by the equation C equals F lambda. In seawater, the speed of sound is approximately 1500 meters per second. The main acoustic quantities used in sonar are pressure, intensity, frequency, wavelength, and sound speed. Underwater sound level is usually expressed in decibels relative to a reference pressure of 1 micro-pascal. These quantities allow us to describe how sound propagates through water and how sonar signals are measured. With these basic sound concepts and acoustic quantities understood, we are now ready to study underwater sound propagation and the working principles of sonar. Thank you.